Humanoid Loco manipulation has made impressive progress, but many existing studies still focus on compact and lightweight objects in household-like settings. Real-world transport looks different. In logistics, construction, and industrial handling, payloads are often heavy, spatially extended, and irregular. This plot quantifies the gap. Existing benchmarks cluster near low mass, small size, and simple geometry, while Unwieldy bench covers the high difficulty region of heavy, extended, and irregular payloads. Specifically, Unwieldy bench include three types of payloads: compact but heavy objects, large regular heavy objects, and large irregular heavy objects. We also combine them with 6 carrying styles, such as front carry, low carry, shoulder carry, and pullback. Together, these form 20 transportation scenarios with different payload placements, moment arms, and balance conditions. We evaluate 4 representative imitation-based baselines. Here is the ladder front carry task. At very light payloads, the controllers can follow the reference and transport the object successfully. But as the mass increases, the same tracking-based policies begin to fail. The payload creates stronger balance disturbances and object support becomes unstable. Here is another task, but the results remain similar. This shows that the benchmark is not just testing whether the motion can be imitated, but whether the controller can remain stable under increasing robot-payload coupling. The key failure mode is shown here. Across different imitation baselines, the joint tracking error, shown in orange, can remain relatively smooth or even low. But the payload-induced angular momentum, shown in blue, grows or spikes before failure. So these controllers are not failing simply because they cannot imitate the reference motion. They fail because the heavy object introduces momentum that is not properly regulated. To test this hypothesis, we make a minimal change to Deep Mimic. We keep the same demonstrations, policy architecture, and original tracking rewards for robot and object motion. The only added signal is this momentum-shaping reward, which penalizes object-induced angular momentum. Across all 4 front carry tasks, DDM consistently improves over Deep Mimic at 5, 10, and 15 kilograms. The visual analysis explains why DDM does not simply reduce tracking error. It keeps payload-induced angular momentum and object angular velocity bounded and maintains a more stable center of mass margin. This supports our main finding. Under unwieldy payloads, momentum regulation becomes critical. For further details and results, please refer to our paper. Thanks for watching.